Our brains are incredible pattern matching machines. But what happens when those patterns lead us astray? When logic takes turn for the bizarre, we enter the world of paradoxes, ideas that seem to defy common sense, yet are provably true. Today, we are going to talk about 3 of the most mind-bending paradoxes in mathematics. Prepare to have your intuition challenged. Imagine a shape, a trumpet, that stretches out forever. This is Gabriel's horn, or Torricelli's trumpet. It's created by taking the simple curve, like y is equal to 1 over x, and spinning it around the x-axis. It gets infinitely long and infinitely narrow, tapering off into the distance. Now, here's the weird part. This horn has a finite volume. You can actually calculate it, and it comes out to be exactly pi. That means you could theoretically fill the entire infinite length of this horn with finite amount of paint. But the surface area of the horn is infinite. So you have enough paint to fill the horn, but not enough paint to paint its surface. How that can be? The secret lies in how quickly things shrink in different dimensions. For the volume, we are adding up an infinite number of tiny, thin disks. The area of these disks is related to the radius squared, or 1 over x squared. This value, 1 over x squared, shrinks so incredibly fast that even when you add up an infinite number of them, the total sum is a nice, neat number. For the surface area, it's different. We are adding up the areas of tiny bands. Their size is related to just 1 over x. This value doesn't shrink fast enough. The sum just keeps growing and growing, heading off to infinity. It's beautiful mathematical quirk where one infinite sum settles down while the other runs away forever. Let me know in the comments if you would like to take a deeper look at the related math. Let's try a little thought experiment. How many people do you need to get into a room before there is a better than 50-50 chance that at least 2 of them share a birthday? Your brain might jump to half of 365, maybe 183 people. That feels logical, but it's completely wrong. The answer is just 23 people. With only 23 people, you've already crossed a 50% probability of a shared birthday. If you get 57 people in that room, the probability skyrockets to over 99%. It's practically a certainty. This is known as the birthday problem or birthday paradox. Why is our intuition so off? It's because we think of the problem from our own perspective. What are the odds someone has my birthday? But the problem is about any 2 people sharing a birthday. We are not checking one person against the group. We are checking every single pair of people. With 2 people, there's only 1 pair. With 3 people, there are 3 pairs. But with 23 people, there are 253 different pairs. The number of opportunities for a match grows quadratically, not linearly, and our brains are bad at grasping this explosive growth. The math is actually easier if you flip the question. What's the probability that no one shares a birthday? The first person has 365 over 365 chance of having a unique birthday. The second has 364 over 365, because one date is taken. Third has 363 over 365, and so on. You multiply all these probabilities together. For 23 people, the chance of no match is about 49.3%. So the chance of at least one match is 1 minus that, which is 50.7%. A coincidence is practically inevitable. Finally, the most famous brain teaser of them all, the Monty Hall Problem. You are on a game show. There are 3 doors. Behind one, a brand new car. Behind the other 2, goats. You pick a door. Let's say you pick door 1. Now, the host, Monty Hall, who knows what's behind every door, does something interesting. He opens one of the other doors, say door 3, to reveal a goat. Then he turns to you and asks the $1 million question. Do you want to stick with your original choice, door 1, or do you want to switch the door to door 2? What do you do? Most people think it's now 50-50, 1 car, 2 doors. It shouldn't matter if you switch, but it does. It matters a lot. You should always switch. Switching doubles your chance of winning. And here's why. When you first picked door 1, you had a 1 in 3 chance of being right. That means it was 2 in 3 chance that the car was behind one of the other doors. When Monty opens door 3, he isn't changing the past. He's giving you new information. He used his knowledge to eliminate a wrong choice from that 2/3 probability zone. He will never open your door, and he will never open the door with the car. His action takes the entire 2/3 probability that was spread across 2 doors and concentrates it all onto the one remaining closed door, door 2. Your door still has its original 1/3 chance of being right, but the other door now holds a 2/3 chance. By switching, you are claiming the higher probability. It's not intuition, it's just playing the odds. As you saw, things can get weird and non-intuitive very quickly. It's important to keep your thinking sharp and remember that there might be underlying logic in many situations. You just might not see it yet. Today we mentioned Gabriel's horn, the birthday paradox, and the Monty Hall problem, but there are many more. If you enjoy this type of content and want to see more in the future, hit the subscribe button. Thanks for watching and see you next time.